From ContainerDays Hamburg, this video is proudly presented by Dux IT.
So hello everybody, I appreciate that you're joining this talk, which covers a topic which we're usually a bit glossing over in the cloud native world, right? So this is all covered by Kubernetes, right? We're setting our cgroups, we're setting our resource requested limits and are happy about it. But yeah, I mean, something has to be there which takes those into effect, and we need to understand that if we're actually running Kubernetes on our own. And that's what we're going to look at today. So just to see where we were at here. So how many of you are setting like Kubernetes quality of service things on a regular basis? OK. And how many of you find the fact that they have a bit puzzling from time to time? OK. And how many of you have to have a look under the hood, how that works actually, how those things work, OK? It's getting like less and less. OK, so if you want to dig into that, then you're in the right talk here. And I want to go into that topic today. So why do I care about all of this? So I'm Tom. I'm an engineer with Mirantis, and within Mirantis, I'm working on cgroups, which, by the way, is like since a few months CNCF sandbox project, which we are very proud of. So yeah, kudos. And yeah, KZOS itself is a certified Kubernetes distribution. So we try to be very like machine agnostic. We try to be like zero dependencies and everything. So we don't mandate anything about like the Linux servers that we're running on, or the Windows servers, if you like. So we need to be prepared for everything there. And that also means that we need to be prepared for different like Linux configurations, and we need to know how to work with that. And yeah, that brings us to the question of noisy neighbors at all. So what is the noisy neighbor problem? I mean, it's, of course, bin packing. So we want to like cram all of our workloads onto as few compute as possible so that we are not wasting resources all the time. And so that has some problems, of course. I mean, the laws of physics apply. So even if we're like in the cloud, I mean, there's still a physical device attached to this. So that means you cannot bend the laws of physics like light speed and so on. So resources are not infinite, and like scaling out takes time, and like rescheduling takes time. All those things come into play there. And yeah, and when you're under load, it might occur to you that your house is on fire because of that. And that's obviously a situation in which we do not want to be in, right? And yeah, that's where Kubernetes comes into play with the quality of service settings. So there where we have to define our resource requests and resource limits and so on. And with them, we tell Kubernetes about our workloads, about our opinions, how to handle things. And together with the Linux kernel, Kubernetes can actually enforce that and like take the right guardrails into place to like make the system smooth or like operate under understandable parameters, even when it's going to be hot, right? So if there is real pressure on the system. And then this is basically where those requests and limits count the most, right? So under usual workload, under usual like load, they're not very interesting. But you know, if you're really making money, so if your servers are burning, then you want to have that in place. So what are we going to look at today? So first of all, we try to understand what Linux containers are and what cgroups are. So how do those connect to each other? And then we want to have a look at how Kubernetes looks at cgroups and uses those things to actually enforce quality of service. And for that, we also need to have a look at the init system, because that init system will have to play a role in this as well. And in the end, we need to like boil all this down to our kubelet configuration, so that we are basically telling kubelet how to integrate with the rest of the Linux node to actually get all all of our stuff into place, all of our resource requests and limits into place, right? So first of all, like Linux containers, this is how it works. Probably not, right? But that's usually how it looks like when you're under contention, right? So everybody is fighting across resources, and the Linux kernel has to like mitigate or like mediate between all of those folks, so they're not like hitting each other to the ground, right? No, yeah, seriously, let's talk about Linux containers. So, short reminder, maybe you all of this know, but this is a Linux container, right? So this is how it looks like. And yeah, I can feel it, I can touch it, so it must be a real thing. But you know, in life there is always somebody with greater wisdom than I have. In this case, it's the person on the right side, which is the Linux kernel, and it tells me there is no container. So what does this mean actually? So containers are a thing that is not part of the Linux kernel itself. It's an emerging thing from lower level kernel primitives. So we have things like namespaces and layered file systems and cgroups. And those are tied together, all together, to form a thing that we call container, but if you want to have a look at the Linux source code itself, there is no notion of it. Linux has no idea what we are doing with it. So this is something that software called container runtimes are introducing on top of the Linux kernel itself. And yeah, and Kubernetes established an interface to that, which is called CRI, which is like the interface between the container runtimes that you can plug and Kubernetes, right? And with this, we're coming to the cgroup subsystem in the Linux kernel. So this is one of the parts which are necessary for us to run containers. And this is basically a huge pile of knobs. So you have a knob for each and every part of your resources. And they're grouped in so-called controllers. So each cgroup controller takes care of a certain resource type and exposes different settings that we can like use as a user on the kernel to like tell the kernel about how certain things should be used by our processes. And they form basically a hierarchy of things, so much like a file system. We will have a detailed look on that later on. And that is actually also like important because like it's all like delegating to each other and like popping up, and we will have a look at that later a bit. And yeah, so the thing is that each process which is running belongs to exactly one cgroup, right? So there is a one-to-one relationship, but each cgroup can have a parent cgroup. So that's the hierarchy I mean, and just like, for example, if you want to compare this maybe with file system permissions, you can set file system permissions on a directory, and then like this delegates down, this trickles down to the leaf nodes. It's the same with a cgroup. So you can basically define certain settings on a parent cgroup, which like confine all the child cgroups. So the child cgroups cannot exceed the settings or the limits that are set on the parent. And they are basically competing on a sibling level with each other. And then there's also the notion of a cgroup delegation, so which means that a parent process can set up a child cgroup for one of its child processes, and put that process into that child cgroup and give the process control to that child cgroup, so that the child process is able to create more and more sub cgroups under that, and like delegate resources, the sub resources below those cgroups. So basically, it cannot exceed the parent cgroup, but it can basically, the resources that are assigned to the parent cgroup, it can further delegate to sub cgroups and do further fine-tuning if we want to. Short overview about the cgroup controllers that the Linux kernel has. So I've just put the most interesting ones in front here: CPU, memory, I/O, PID, Those are the ones which are probably most familiar, or which you probably have an idea of what they can do. Then there is many more which are not interesting right now in this talk, but just to let you know that there is a lot of different cgroups, right? Cgroup controllers out there. And the cgroup controllers themselves, they're exposing certain settings, which usually are in this dotted notation, and they are very much dependent on the cgroup controller itself. So usually the naming pattern is controller name dot value. So in this case, the cgroup control, the CPU controller has a setting called wait. The memory controller has a setting called max, and then you can set a certain value on those settings, and they have a special meaning depending on which setting they are. So we have basically one thing to note here is that we have typically two types of settings. One is limits, so this is like absolute values, and the other one is weights, which is like a proportional value. In this case, CPU weight is a proportional value, which is very much important for what I will be showing you next, because in Kubernetes, we're defining absolute values. So we say one CPU, we are requesting one CPU. How does that relate to a proportional setting, right? This is one of the problems that we want to understand today. Okay, so now that we have a broad understanding what cgroups are and what controllers are there, and we want to have a look at the CPU and memory controller and how they interact with Kubernetes and how Kubernetes itself views the state of the world concerning that. Kubernetes, as I said before, has the notion of quality of service classes, which is something that we are not defining ourselves. This is deduced by Kubernetes itself by the resource requests and limits that we set. And there's like three QoS classes. The best effort one means basically YOLO, you don't set anything there, which also means that you're not guaranteeing anything there, and those pods are basically just as this best effort. So whenever there's time, they will be scheduled, but if there's resource contention, then they will be most likely the first ones to suffer from this. Then we have the other extreme, which is the guaranteed QoS class, which is basically resource equals limits, which in this case means that you're basically blocking those resources on the node itself, but you cannot even exceed those. So this is basically guaranteed. So if you're setting resource requests and resource limits identical to, say, 2 CPUs, 5 gigabytes, then you will have those 2 CPUs and never more. So this is already a trade-off because you cannot burst, which is like the middle ground. So you have some requests, some limits, but they're not equal. So this makes the most valuable QoS class, I would say, because those give you the possibility to burst and to use more CPU or more memory than they usually should request. But if there's still something available there, that's just fine. I mean, we just don't want to have slack CPU around, right? So we want to use it if we can, right? Okay. This is how Kubernetes organizes our workloads in the cgroup hierarchy. So we have the cgroup root for Kubernetes, for the kubelet, and for all of our workloads is like by default called kubepods. So this is basically the root cgroup under which kubelet will organize all of our containers and pods and whatnot. And then you see that you have like those 3 quality of service classes already shown here in the color-coded way. So we have guaranteed, burstable, and best effort. And to note is that burstable and best effort both get a sub-cgroup assigned, where basically everything is summed up. So from bottom to top, kubelet will go on and sum up all the resource and requests of each container. Then it will go sum up all the resource and requests of each pod, and it will sum it up until the top level for best effort, and then, or not for best effort, sorry, for burstable, and then it will set those values for burstable. And the same for the guaranteed pods. Best effort, in this case, doesn't get anything set, so it's just like best effort. So there's no requests and limits, and like the kernel will just do something with it. And also noteworthy is that the guaranteed pods themselves don't have a cgroup in front of them, so they are directly attached to the root kube pods cgroup, which means they are directly competing on the same level on all the other burstable and best effort nodes. So directly competing to each other. This is important because resources are distributed amongst siblings. So the kube pods cgroup has a certain setting, and then this is like proportionally distributed amongst the sibling cgroups. That means that all the burstable pods are just worth as if there would one guaranteed pod like them. So this is like already like constraining the resource allocation that burstable pods can do compared to guaranteed ones. And that's also like the precedence, right? So from bottom to top in this picture, like they're more important, right? And used by the kernel. Okay, the actual mapping from Kubernetes resource requests and limit to cgroup settings looks as follows. So we basically have the CPU limits, which are affecting the CPU.max part, the CPU.max setting on the cgroup level, which is basically a throttling in 100 millisecond slices. So you're basically putting a nanosecond or a millisecond value on this, like 50 millisecond, this is basically half a CPU. So you get 50 milliseconds of a 100 millisecond CPU time slice, this means half a CPU. And if you're having 3 CPUs, you would get 300 milliseconds of a 100 millisecond time slice. So this is how limits on CPU basis work. Then we have the proportional CFS setting, CPU.weight, which is for the CPU requests. And this is a very tricky part, because like in Kubernetes, we have absolute values, but the Linux kernel doesn't understand absolute values. It has this proportional calculation for CPU.weight. So I can put any number between 1 and 10,000 into it, and it will just sum up the weight of all the sibling C groups, and then just do a proportional weight. So if I'm putting if I have 2 C groups and one has a CPU weight of 1 and the other has a CPU weight of 2, this means like 1/3, 2/3 distribution. And if I'm setting 2 and 3, then I have 40%, 60%, right? So this is like just math, right? So you're just doing relative limits. So that is already a problem, because you just cannot translate those absolute Kubernetes CPU requests into absolute CPU requests on the CPU weights on the Linux kernel, because it doesn't work like this. So there's a real magic formula inside Kubernetes, which we'll look at later in the next slide on to do that. But let's have a short look about about memory. So there is the mem-max setting, which is basically just the absolute amount of bytes which you are allowed to use in your C group. And this is a bit different from the limits in CPU, because CPU, when you're hitting your CPU limits, you're getting throttled. When you're exceeding your memory limits, you're being OM killed. That there's no notion of like trying to request memory but not getting it. The Linux kernel will just get you the amount of memory that you requested, but then you're probably eligible for OM kills, and then your process will just be terminated because it was using too much memory. So this is basically a very important difference between both settings, because when you're hitting your CPU limits, you're just being throttled. If you're hitting your memory limits, you're being killed. The memory requests themselves are not propagated to the Linux kernel as of now. There is a cap open, which is actually using certain kernel settings which are not related to cgroup, which are a per process setting, which is called OM score adjustments. Right now, the memory requests are only used for Kubernetes scheduling decisions, but they're not used for or they're not enforced in the kernel in any way, modulo the cap that I mentioned there. So if you're interested in that, please dig into that, but that is not related to cgroups. This is working differently. Now this freaking formula down below in the right corner. So if you want to know what the CPU weight will be that your cgroup receives deduced from your Kubernetes CPU requests, then you have to use this formula. I've just tried to illustrate that in this example. So on the left side we have CPU requests. Which are and the ratio which you should expect. So if you're summing this up and taking the relative ratio of that, then you get 0.7, 2.86, and so on and so forth. And then on the right side we have the actual CPU weights as calculated by the formula below. And then you see the ratios don't match up. So there's already a bit of discrepancy between the absolute requests that we get and that we set and the relative CPU weights that are being calculated. So this is an inherent problem, an inherent mapping problem. Right. So you see the factor here is also different. I'm putting 10 times more CPU there from 100 to one full CPU, but I only get 8 times more on the right side. So this is something that you need to be aware of. Right, so that we know how Linux and Kubernetes use cgroups. We also need to know how the init systems use them. And what is the init system at first? It's the PID one, right? So the Linux kernel boots up, and then it pivots all of its duties to PID1, and the PID1 has to do all the rest. So this is the only process that the Linux kernel itself starts when it's booting up. And so the PID1 has a very crucial role, of course, because it has to bootstrap the whole computer, right? So it has to start all the node components, all the components that are needed, I don't know, logging and SSH, and also Kubernetes worker components. And it's also controlling the lifecycle. I mean, you probably get the idea what an init system does. And guess what? It, of course, integrates into cgroups as well. So we have to have a look at that. What kinds of init systems do we have? We have some historical ones, some simple ones, OpenRC is kind of simple and popular for its usage in Alpine, for example. And then we have some dominant ones here. But the dominant ones might not be so simple. Systemd is the only really dominant one that we have to have a look at if we're not running, for example, on Alpine or Gentoo or something. Then we have to have a look at that. So this is actually a really complex beast. Systemd has its very own understanding of how cgroups are to be used. And it has very idiosyncrasy. It has some idiosyncrasies about how cgroups should be structured, and it even wants to own everything. So you shouldn't be going to the Linux kernel and modify your cgroups per se by yourself. You have to do it via systemd. So the systemd has its own dbus API to do that. And if you want to be integrating on a systemd managed system, you need to basically use the systemd APIs instead of the standard Linux kernel ones. And right. The classic one. This is basically this slide, which I just took in front. Right. Okay, so how does it look in practice? So this is basically a hierarchy of systemd managed, the cgroup hierarchy, I must say, of a systemd managed Linux computer. So we have the root cgroup, and then we have the system slice with all the system components, all the OS process threads and so on. Then we have a user slice, which covers all the user sessions. And then we have the kubepods slice. And we also see the nomenclature that we're enforcing here. But the dot slice is basically enforced by systemd. It wants to have that. Suffix, and it has a special meaning. but yeah, so this is how it looks like. And then we have on the right side, like a deeper look in the kubepod structure. And this is basically the stuff that we've seen before in a former slide, but just in the systemd notion, right? Then we have the same on the OpenRC side, which is very much simpler. You have the kubepods on the root directly, and then you have all the system services as siblings. So there is no like deeper hierarchy that you had before, right? So we need to configure that on the kubelet, actually. So what do we need to do there? This is how kubelet views the state of the world on the node. So we have like three groups. We have the kube reserved, the system reserved, and the pods groups. So the pods group is the group that we've already looked at. Kube pods, system reserved, and kube reserved are pretty much mapping to the stuff that we've already seen on the systemd side. So system reserved is typically mapping to the system slice on the systemd side, and kube reserved is for things that scale with the number of pods, right? And in this case, it's the pod. It's usually like kubelet and the container runtime. And the node capacity or the node the actual allocatable resources are deduced from those settings. So the kubelet takes the things that we reserve for the system, the things that we take that we reserve from the kubelet, and for the kube group, and deduces that from the node capacity, and that's actually the resources that we can allocate to pods. And that's how we basically tell the kubelet how to do it. So first of all, we need to have the cgroup driver in place. So we need to tell kubelet that we're actually on a systemd managed node. So it will take all the idiosyncrasies of systemd into account. So for example, it will use the systemd dbus API to manage the cgroups instead of going to the Linux kernel primitives for this. This is actually something that can nowadays be read out from the container runtime. The container runtime has to be configured in the same way because it also has to deal with cgroups. And in recent Kubernetes Kubernetes versions, Kubernetes is able to pull that value from the container runtime. So you don't have to do it twice. So you have to do it on the container runtime, and then kubelet will know about this. And then you can basically say, define the resources for the system and kube reserved cgroups in the same way as you would do for single pods. And now the most important part is the enforce node allocatable setting, because by default, kubelet is not setting those settings to those respective cgroups, so kube node and system. It's only setting the cgroup settings to the kube pods group. And this is a problem because as we learned, the CPU weights are relative. And if you're just leaving the kube node and the system cgroups at their default levels, they will not match with the things that are calculated for the kube pods. So this won't align. So you will end up with potentially way less resources for your system than you would expect, because it doesn't align with what kubelet calculates for the kube pods, because it's a relative thing. The default value for CPU weight is 100, and according to the formula, if you have many CPUs that you're allocating, then you're getting in trouble. So this won't align. Yeah, so let's wrap it up real quick, because I'm running out of time, of course. So what do we need to know? What is the core of this talk? So the cgroup layout actually has practical implications on our workloads, especially when they are under contention. The CPU weights are proportional in the kernel, whereas they are absolute on the Kubernetes level, and that has to align even for things that are not Kubernetes managed, right? And if you're not doing this, then your quality of service settings are not enforced in the way you would expect them to be enforced. And that is way, way, way important. So how do you configure your quality of service? I mean, it depends on your workloads, right? So there is no good answer to this. You need to understand what you want to be doing with your workloads. You have to you have to make best guesses, and then you like to have monitor and experiment with it. And there is probably no right or wrong. You just have to find your sweet spot, and that you can only do by experimenting. And one final take. I've been warned a lot of times by linters and cluster scanners about missing resource limits, and that I should add those. And my take on this is that I don't need to, because my CPU requests, if I have them in place, and memory requests are already enough to tell the kernel to do the right thing when I'm under contention. Why should I set limits and constrain my resources or constrain my workloads if they still can schedule stuff, right? So if there's still CPU cycles available, right? Okay, thank you. That's all I have.
There's always a discussion about should we put CPU limits or not. And we can read a lot about it. Some people will tell you you should, some people will tell you you shouldn't. What's your take on this?
I mean, this is basically what I tried to convey with that slide. So I don't think that CPU limits are actually needed if you get your CPU requests right. Because that's what's like enforced under contention. Your CPU limits are always in effect, even if there's slack CPU, right? So usually you can get away without them and just be sure that the kernel will just enforce it when it's needed.
Okay. We have one question over there. Are there plans to add support for the other C groups like I/O?
Yes. I think there is caps out there, and maybe there is even like already GA or beta support for things like I/O and certain things. But this is like, again, a whole different topic, and I think like CPU and memory is the 99% use case. And yeah, but there is, of course, like if you've seen with the memory request stuff, there is also like a cap open to make that to propagate that to the kernel, and as well there is for the other C groups. And I think that like there is also like device memory, so for graphic card memory and stuff like this, and there might be also like already some support for it, right?
Okay. Any one last question? Nobody in the audience? Come on. Okay. Well then, thanks a lot for your talk. It was very interesting. A round of applause for our speaker, please.
From ContainerDays Hamburg, this video is proudly presented by DAX IT.